The paper delves into the twisting of uneven ropes, comprising two circular strands with different diameters. This concept has been briefly addressed in the literature, including examples such as wire ropes and Viking neck and arm reins. The authors introduce a deformation parameter epsilon, where the diameter of one strand is denoted by d and the other by d equals 1 epsilon d, with 0 is less than or equal to epsilon less than 1. The center lines of the rope are assumed to form simple helices, with the d-strand centerline twisting around a cylinder of radius a and pitch h equals 2 pi h, parametrized by r equals a cost, asint, ht. The d-strand centerline is twisted on a cylinder of radius a, with parametrization r equals a cost, asint, ht plus delta. The pitch angles of the two strands, v up tack and v up tack, are related by tan v up tack equals tan v up tack, 1 epsilon d, 2a. The ratio of the cylinder diameter to the strand diameter, 2a, d, is a function of both v up tack and epsilon, and its determination is described in the appendix. This ratio approaches 1 for parallel vertical strands, v up tack right pointing arrow 90 degrees, and approaches infinity for parallel horizontal strands, v up tack right pointing arrow 0 degrees. The length of the rope, Lr, obtained by twisting two strands of length Ls, is given by Lr equals Ls, sin v up tack, and the number of turns, Nr, on the two-stranded rope is Nr equals Ls, 2 pi a cos v up tack. In the context of rope mechanics, the rope curve plays a crucial role in characterizing the behavior of twisted ropes. For a classical rope, the rope curve displays the function of Nr, with the apex corresponding to the maximally twisted geometry. However, when dealing with an uneven rope, where the two strands have different lengths, the scenario becomes more complex. Equation 1.2 reveals that v operator up tack greater than or equal v up tack, indicating that if twisted from two strands of even length, we will have L operator r is greater than or equal to Lr. Figure 1 illustrates the d-strand pitch angle v operator up tack as a function of d-strand pitch angle v up tack, as well as the ratio L operator r, Lr, with the parameter e varying from 0.0 to 0.5. This analysis underscores the significance of the parameter e in determining the rope's properties, particularly the maximum number of turns and the zero twist pitch angle. The rope curve for an uneven rope is critical in practical applications, especially in the context of wire rope, where understanding the rope's behavior under varying conditions is essential. By examining the rope curve, researchers can gain insights into the rope's mechanical properties, such as its maximum twisting capacity and stability. The parameter E, which represents the unevenness of the rope, plays a pivotal role in shaping these properties. As E increases, the rope's behavior deviates significantly from that of a classical rope, highlighting the importance of considering unevenness in rope design and analysis. The paper delves into the geometry of ropes, specifically focusing on the uneven rope model where strands of different diameters are intertwined. A mathematical analysis is presented, demonstrating that this structure can be mapped to a non-Euclidean surface of two-dimensional space with constant negative curvature. This mapping enables the calculation of various geometric properties, such as the length of the rope at the apex point and the zero twist pitch angle. The concept of the rope curve is introduced, representing the relationship between the number of turns and the length of the rope at the apex point. It is shown that as the difference in strand diameters increases, the length of the rope at the apex point decreases, and the zero twist pitch drawing from both theoretical physics and historical practices related to rope construction. In summary, the table on page 4 presents key findings on the relationship between the zero twist pitch angle and the deformation parameter, providing valuable insights into the structural properties of twisted filaments. The reference to the maximum observed in Figure 1b and the acknowledgement of contributions from experts in the field underscore the importance of this research in advancing our understanding of complex geometric structures. The research paper discusses the application of advanced machine learning techniques to improve the accuracy of predictive models in environmental monitoring. Specifically, it explores the use of ensemble methods to combine the predictions of multiple models, enhancing their overall performance. The study highlights the importance of data preprocessing and feature engineering in preparing datasets for these models. It also emphasizes the need for continuous model evaluation and adaptation to ensure their effectiveness in real-world scenarios. This appendix extends the previous work on two-stranded ropes by deriving the mathematical formulation for the geometry of uneven ropes. The distance squared between 2 points on the D and D strands is given as increment 2, t, equals 2a2e add plus e2d 2 quarters, 2a2e add, cos t, plus ht plus delta, 2, where t is the difference in angles between the 2 points, a equals a ed, 2, and h equals h. To satisfy the twisting rope conditions, the distance between the two ropes must meet increment equals d, 2 plus 1e, d, 2, and the derivative of increment 2, t, must be 0, leading to equations, a.1, and a.2. These equations are solved numerically for t and d, 2a to obtain the geometry of the uneven rope. For e equals 0, these equations have been solved previously, but for e does not equal 0, both equations must be solved simultaneously. The curvature condition to prevent self-intersection is also modified for the uneven rope, becoming d is less than or equal to 2, kappa, which can be expressed in terms of the pitch angle v up tack. The condition for the uneven rope to avoid self-intersection is derived, resulting in the inequality, 1 minus e, d is less than or equal to 2 kappa asterisk operator, where kappa asterisk operator is the curvature of the d-strand centerline. This condition is rewritten as 2a, d is greater than or equal to 1 minus e, a kappa equals 1 minus e, 2a minus ed, minus 2a plus ed, squared plus 4h squared, equals 1 minus e, 1 minus ed, 2a, 1 minus ed, 2a, squared plus h, a, squared, as shown in equation, a.6. Figure 4 illustrates the ratio 2a, d as a function of the pitch angle v up tack, with the limiting curves for bending shown in black. The curves do not intersect, indicating that self-intersection of the uneven ropes is avoided. The volume fraction of the uneven rope, Fv, is defined as the ratio of the volume of the two uneven strands to the volume of an enclosing cylinder. The expression for Fv is derived as Fv equals 2a, d plus 1, 2, a squared, h squared plus 1, squared plus 1 minus e, squared a squared, h squared. 1 minus ed, 2a, squared plus 1, squared, as shown in equation, a.7. Table 2 presents the resulting pitch angle corresponding to optimal packing, Cp, as a function of the deformation parameter e. The table shows that the close-packed pitch angle decreases as e increases, while the volume fraction exhibits a non-monotonic behavior.